Hello, good day everyone. Today is another class of physics. This class or this presentation is for grade 12. Subject is physics. We still at chapter 4, forces, vectors and moments. Our presentation today will cover 5 main parts, which they are center of gravity. We will say what's the gravity and what's the center of this gravity. Number 2, finding the center of gravity. We will try to find the center of gravity of different shapes or different objects. Number 3 is turning effect of a force. So what's the turning effect of any force? Number 4, moment of a force. And finally number 5 is balanced or unbalanced. So we will start on first topic, which is center of gravity. Before that, please open your book on page 62 and try to have a look there and here on this presentation. As we can say or there in your textbook, we have a weight. Every one of us have a weight because of what? Because the force of gravity. So if the gravity is there, so there's a weight. This weight, it comes from what? Force of gravity. And force of gravity, it comes from where? Gravity of the earth. The gravity of the earth. So the gravity of earth, it causes a force on what? On any object. Or known as a weight. So we have a weight because of what? Because of force of gravity of the earth on us. Okay. Each part of our body experiences what? A force. This force is caused by what? Of gravity. So in each point or each part of your body, there is what? There is a force. This force is caused definitely by what? Gravity. If there is no gravity, there is no weight. Like when you say someone outside of the, what do you call, the space, out of space. So there, when the gravity is equal to 0, so definitely the weight is equal to 0. However, it's much simpler to picture the overall effect of gravity as what? As a single point. As a single point. This single point is known as what? Center of gravity. So the center of gravity is a single point. So what's the definition now of gravity or the center of gravity? Center of gravity of any object is defined as what? As a point, as we can say here, as a point where all weight of the object may be considered to act. So the center of gravity of an object is defined as a point where all the weight of the object may be considered to act. So the conclusion of this slide, what's the conclusion? The conclusion is there is a weight because of what? Because of gravity. Okay. Okay, now we will say some different objects and where is the center of gravity of those ones. As we can say here in this figure here, for any person standing upright, so the center of gravity is roughly in the middle of the body, is here. In the middle of the body is here. It's exactly behind what? Behind the navel. It's here. So the center of gravity of this man from this side is here, which is exactly here. So this is the center of what? Of gravity. If we take another shape like this one, so where is the center of this one? Center of gravity, it will be where? In the middle. So the center of this in the middle, the center of this is the middle here. So we can say there the center of gravity, it depends on what? Depends on the object itself, the shape of what, of any object. So the shape of any object, we're gonna define what the center of gravity. Take another example. So another example of the center of gravity, as we can say here in this figure, we can say there is a center of gravity of some shapes, like a person, like a circle, like something, and there is another center of gravity for objects or non-uniform objects, as we will say in next slide, like this one. So if we take a look here at this person, so we can say it's much easier to solve problems if we simply indicate an object's weight by a single force acting at the center of gravity, rather than what? A large number of forces acting on each part of the object. So if we find a single point or a single force acting on this object, or the weight of this object, it's much easier to solve many problems by using the center of gravity rather than using a large number of forces acting on each part of the object. As you can see here in this figure, it's figure 14 in your textbook, we will say this point or this figure gonna illustrate this point. As we can say here, the sportsman here performs a very complicated movement. It's a very complicated movement. The weight of this person could be start at any point here, going through this, here, any point here. It's a weight. It's a weight of what? Of his body. But as we said here, it's much easier to solve problems if we what? Indicate a single force acting. So this sportsman, however, he can say that, or we can say that the center of gravity follows a smooth path through the air. It's a smooth path. It's like this. He start moving from here, up to where? Up to here. So the center of gravity, it will be here. Center of his weight, or where the gravity has the much stronger effect, it's here. So this is for, as we said before, this is a shapes or a center of gravity or of some standard shapes, circle, any other shapes. So if we go through some random shapes, so we need to find the center of gravity. So next topic, it's on page 63, how we could find the center of gravity of what? Random shapes or objects, any object. So finding the center of gravity of random object, how we can find it? So the center of gravity, for example, like a tin sheet, okay, can be found by what? Suspending it freely from 2 to 3 points. So this shape here, we're gonna suspend it from, for example, at least 2 points. We can take 2 or more, or 3 points. Even 2 is enough. So this first point here, and this is the second one here, and this is the third one here. What we will do, we will suspend this object freely from first point, and then we'll leave it moving until staying. After this object is staying, no more movement. So then we will put what? Plumb line. We will hang plumb line from this point here. So this plumb line will still moving until staying here. So we will mark a point here. We will put like a point here, and then we will draw straight line from first point to this point. Then we will hang it or suspend it from where? From the second point. And then we will do the same. We'll leave it, the object moving until staying, and then we'll put plumb line here on the second one, and then put another point. Okay, so this is the way of how finding the center of a gravity. So as we can see from the next slide here, small holes are made around what? Around the edge of a regularly shaped. This shape is random one. A regularly shaped object. First, this first point. Second, a pin is put through one of the holes and then firmly in clamp and stand. So the object can swing freely, swing until a stop. Then a length of string is attached to the pin. The other end of the string has heavy mass attached to it. So the arrangement, this arrangement is known as plumb line, because we use what? A plumb line. This arrangement is, as we discussed in the previous slide, it's a plumb line. So the object will stop swinging when its center of gravity is vertically below the point of suspension. So this one, the object here, is stop swinging when its center of gravity is vertically below the point of suspension. Then, as we said in last slide, a line is drawn, as we can see here in this figure. A line is drawn on the object along the vertical string of the plumb line here, and then the center of gravity must lie on what? On this line. It will be somewhere in this, on this line. To find the position, exactly the position of center of gravity, the process is repeated. Where is repeated? With the object suspended from the front holes. So we do it for as we did in last slide. We did it with this holes, and then the second one. At least we should do it with 2 holes here, and then another one, for example, here. So from the front holes. So where is the center of gravity? The center of gravity will be at a point of intersection of the lines drawn on this object. So to make all of these things clear, we will show you some video, short video, determine the position of center of gravity. All things discussed here in this slide, or how to find the center of gravity of a regularly shaped or random one, we will show you some video on this, or how to do that. So please have a look, and then we'll be back. So first step, we will make what? 2 holes. This is the first hole, and this is the second one, as we said in last slides. So then what? So now we will suspend it from first hole and leave it swing freely. say, okay, swing, swing, swing until stop. Then suspend plumb line here, say we will point this point here, and then we will draw straight line from the hold until that point. Okay, now we will do the same with this hold, the same procedure with the other hold. Okay, as we see watching that video, so where is the center of gravity? The center of gravity is the intersection here between the two lines. This is the first line, for example, this first hole. So this is the line with plumb line, and this is the second hole, and this is the line with plumb line. So the intersection here, intersection is what? Center of gravity. This is the center of gravity. Okay, now we will say another subject, which is the turning effect of a force. So what's the turning effect of a force? As we can say here, so any force or forces can make things accelerate, can make object turn around, can do something else as well, many things as well. So we can say that they have what? Any force, they have a turning effect, a turning effect. So what's a turning effect? As we can see here in this figure, to maximize this effect of the turning effect of a force, of any force, we need to maximize it. For example, in this figure here, where is a mechanical try to turn the nut here, he trying to close this way or open, same. So the turning effect here, the operator pulls close to what? Close to the end of a spinner here, of the spanner here. So the spanner here, he trying to push where? Here, at the end, as much as possible. So the operator pulls close to the end of the spinner, as far as possible. From where? From the center of the nut here, from the center of this one. He trying to close or open it. So to maximize the effect of or turning effect, first he need to push where? Here at the end as much as possible, at the end of what? Of spanner. This first thing. Second thing is trying to make what? Angle of what? 90 angle of 90 degree with what? With the spanner. So as much as you can, try to make this angle 90. If you make this angle 90 and put your hand as much as far from the center of this one, so the turning effect will be high, or the force of turning effect will be increased. Okay, now we will need to know about the quantity of turning effects. What's the quantity of turning effect that tell about this force? So we will move to moment of a force. The quantity which tell us about the turning effect, so there is any quantity telling us about what? Turning effect of what? Of any force. So what's that? That is a moment. That is a moment. So the quantity which tell us about the turning effects of any force is known as what? A moment, or a moment of a force. So any moment, or the moment of any force, depends on two quantities. Depends on two quantities. First one is a magnitude. So the magnitude can affect in this way. The bigger the force, the greater its moment. So the bigger the force, the greater its moment. Then the perpendicular distance of the force from pivot. So that this distance from the pivot, the further the force act from the pivot, the greater its moment. So as the distance is much or is higher, so the force is higher. So the moment of a force will be defined as follows. The moment of a force, the definition of the moment of the force, or how we can find the quantity of it, the quantity of moment of a force. The moment of a force of the quantity is equal to the force times perpendicular distance of the pivot from the line of action of the force. So we will take some examples to make those things more clear to you. Okay, now as we can see in figure 17, we will go through those quantities, or how we could find those quantities. As we can see in this figure here, the quantities, first one is F1, first quantity is F1. Where is F1? This is an F1. F1 here is F1 or F2 is the same. They are quantities but in different ways. As we can see here in figure 17a, the force F is pushing where? Down on the lever. So the perpendicular here distance, which is x1. So the distance from the pivot here, this is the pivot, this is the pivot here. So the distance from pivot until here, until the F, is known as x1, which is perpendicular distance, which is x1 here. Then the moment of force, so how we could calculate the moment of the force here, F1, about the pivot, is given by moment is equal to force, which is here F1, times what? Distance from where? Pivot. This distance, which is x1. So the moment here is equal to what? F1 times x1. F1 times x1. This one is different. This figure here, P, because the force is not vertical on x1, there is an angle here. So it's different from this one. And we will see how we could calculate the moment of this. So to conclude, the moment is equal to force times distance. Distance from where? From pivot. So moment here is equal to F1 x1. F1 times x1. What's the unit of a moment? The unit of a moment is now is what? In Newton meter. It's in Newton meter. This unit, which doesn't have any special name. It's not ohm, it's not ampere, it's not a coulomb. No, it doesn't have any special name or famous one. It is just said, or can say, Newton meter or Newton centimeter. It could be by meter, it could by centimeter, because it's what? Force, distance. Distance could be in meter or centimeter. Okay, now I think all these quantities are clear except this one. So it's different of calculation. The moment is different to calculate. So before we move to this one, we will take a quick look to some demo here to understand those quantities more clear. F1, x1, pivot, perpendicular, and other things. So please watch this video. This video is about a moment. Set a spanner to fix a nut. This is a child using a seesaw, or this. So what's the moment? The moment is a turning force around the fixed pivot here. This is the pivot here. The pivot is here. It could be here, could be here, could be here. So we have pivot here. Say now here. What will happen here? We have lots of things to consider in this figure. So if we consider this guy or this boy here, as we can say here, this guy is heavier than this one. This guy is heavier than this one. So from at first look, or when we take quick look, we will say this guy will make this thing down and this one will move up because this one is heavier than this one. Okay, and we have another thing to consider here, which, so first one is the weight. There is two things to consider in this figure: the weight of each one, and then what's the distance from where pivot here until the center of the force. This is a force because there is a weight, force of weight. And then the distance from here up to here. For example, this is an x1, this one is x2. So now, as we said, if you take a quick look, we will say this guy will go, down, and this one will move up. But this one is not happen. Why? Because the distance here is bigger than the distance here. Say now. So to make those things balanced, or this seesaw is balanced, what will we have here? We have like 500 Newton weight and 2 meters. Say now. From the pivot, and the heavier one need to be closer. Yep. So moment is equal to force of distance. It will be 1000 for this one, and heavier one, it's 1000 multiply 1, it's also 1000. So the seesaw is balanced. Yes, the measuring is by using Newton meter, distance by meter, force by Newton. Yep. Another example is here. Say there's 10 Newton here, 10 centimeter, because this is centimeter. It could be 3 meter. Yep. So we can use this formula here to find force is equal moment divided by distance. Distance is equal moment divided by force. Moment is equal force times distance. And there's two questions here for you to try. Just try to solve those questions. Say, calculate please. Yep. So for the seesaw, we have two moments. It's clockwise moments, and the other one is anti-clockwise moment. So balanced is equal to clockwise moment is anti-clockwise moment. Yep, it could be Newton meter. Yes. Okay, now we will solve some examples at the end of this presentation to make those things more clear. Now we will move to figure 17b. 17b here. This figure shows a slightly more complicated situation because the force is not or doesn't make angle 90 with the distance here. So as we can see from this figure, what we will say here, F2 is pushing at angle what? Theta. There's an angle theta greater than what? 90. This makes it have less turning effect, so the effect of the turning is less because the angle is not at 90 degree. So this makes it have less turning effect, so the turning effect will be less. There are two ways to calculate the moment of the force. There are two methods here. We will discuss them separately. First one, or first method, what we'll do, we will draw perpendicular line from the pivot to the line of the force. This one. We will do a line from where? From the pivot here until the force here. So this one is called what? X2. X2. It makes angle what? 90 what? With the force. So first one, draw perpendicular line from the pivot to the line of the force. Then this first one. Then find the distance x2. Find the distance x2. x2 is equal what? x2 here from math. It's easy. x2, as we can say here, is equal what? This distance d sine theta. D sine theta. So we already have what? x2. Then we calculate what? The moment. The moment is what? F2 times x2. F2 times x2. And x2 is what? D sine theta. D sine theta. So the moment of the force is equal to F2 d sine theta. This one, it's very easy. What to do? First, draw the line from here to the force here, which made an angle of 90. Then find the distance x2. x2 is equal to d sine theta. Then find the moment of a force, which is equal to F2 times what? x2. x2 equal to d sine theta. So the final one is F2 d sine theta. Okay, now we'll move to the second one, or second method. The second method is slightly different from method 1, but we will give exactly the same result of method 1. So the method 2 is depends on how to calculate the components of F2. This is F2. We need to calculate the component of it, which is at angle 90 to the lever here. So this is F2. This component is F2 sine theta. F2 sine theta times what? D times D. So the moment is equal to F2 sine theta times the distance, this distance D, which is exactly the same of method 1. Moment of force is equal to F2 d sine theta. F2 d sine theta. So it's same. We can use method 1 or method 2. Method 2. This is for figure B. Figure A is easier than this one. So now we will move to balanced or unbalanced topic or subtitle. Now we can use the idea of the moment of a force to solve two sorts of problem. This is one advantage or some advantages of what? The moment or a moment of a force. So first we can check whether an object is remain balanced or start to rotate. Two, we can calculate an unknown force or distance if we know that an object is balanced. If we know the object is balanced, so it's easy to know what the force or distance which was unknown. We can use this balanced here, the condition of balanced, to find any one of them, force or distance. The second one, this is the second one. First one or first advantage of this one is we can check whether any object will remain balanced or start to rotate. So we can use the principle of the principle of a moment to solve those problems. The principle of a moment states that for any object, as we said before, that is equilibrium, means all forces equal, the effect of forces is in equilibrium. So the summation of clockwise, as we said before, clockwise moments about any point provided by the force acting on object is equal to the summation of anti-clockwise. As we saw in seesaw, the force which is clockwise is what? Equal to the summation of moments of this one is equal to the summation of anti-clockwise moment about the same point, which are started from the same point, as we say in the seesaw. The seesaw is like this, so this will move it. This guy will move this way, which is clockwise, and this acting where at the same point here, and this one will be anti-clockwise. So any object which is in equilibrium, so the summation of clockwise moments is equal exactly to the summation of anti-clockwise, because, or the condition of that one, what is, and which they are in equilibrium or balanced objects. If they balanced, so this one is equal to this one. If not balanced, no, this one is not equal to this one. They will be different. Now we will do some worked examples to make those things more clear. So as on your textbook, I don't know what's the page number, worked examples. Number 2, say this figure here. This is the seesaw, it's like a seesaw 1. This is the pivot here. So we have an object here which is 40 Newton, another object here is 20 Newton, and the distance here is much it's much than this one. This one is 1 meter, it's 2 times this one, it's 2 meter here. So in the seesaw shown in figure, this one, figure 18, which is in equilibrium. Equilibrium mean balanced, or will start to rotate. So the question is the seesaw balanced or start to rotate or moving? Okay, now to say or to determine if the seesaw is balanced or not, what we will do, as we said before, we need to, so the condition of balanced is what? The clockwise moment is equal to what? Anti-clockwise from here. Clockwise from here is equal to anti-clockwise force or moment. So we will work this one individually. we will find this one first, clockwise, the moment here, and we will find this one, and we will say then the quantity of each one. So this one, the CSU, will remain balanced. Finally, will remain balanced. But we need to prove that. Because what? Because the 20 Newton here force is twice what? We can say without any calculation. How? This force here is 20 Newton and this force here is 40 Newton. Okay. But the distance from this one up to here is 1 meter and the distance of this one is 2 meter. So it will be balanced. It will be balanced. Because the 20 Newton force is twice as far from before as 40 Newton. But we need to prove that by calculation. We need to determine the anti-clockwise moment and the clockwise moment and say the result of each one. So to prove that, we need to think about each one or each force, clockwise and anti-clockwise, individually. Which direction is force trying to turn the CSU, clockwise or anti-clockwise? The 20 force here, the 20 force is tending to turn the CSU anti-clockwise. Why the 40 Newton force is tending to turn it clockwise, as we draw here. So step 1, we need to find them individually and then compare the result of each one. First, we need to determine the anti-clockwise moment. The anti-clockwise moment is equal to what? 20 is a force F times distance. For example, let us say x1. Let us say this one is x1, this one is x2, this one is f1, this one is f2. So this one is for clockwise moment, and the force of or moment of clockwise is equal to f2 times x2, and anti-clockwise is f1 times x1. This one. So moment of anti-clockwise force is equal to 20 what? Newton times 2 meter. It's equal to what? 40 Newton meter. Step 2, we will do the same for this part, or clockwise moment. So the moment of clockwise force is equal to 40, this one, times the distance here, which is 1 meter. So it's equal to what? 40 Newton meter, which is exactly same as this one. So we can say that clockwise moment is equal to anti-clockwise moment, so that the CSU is balanced and therefore doesn't rotate. Why? Because the CSU is in equilibrium or balanced. So this one will balance this one. So this is for today. I think we finish the class or this presentation. Next class we will continue with some more examples. So thanks for listening. If you have any questions, please try to contact, and I'm free to and happy to answer your questions. Thanks and good luck.